Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1901 marks a pivotal moment in the history of medicine, a year when Karl Landsteiner published on agglutination, phenomena of normal human blood, a paper that would fundamentally alter our comprehension of blood and consequently revolutionized transfusion medicine. Prior to Landsteiner's groundbreaking work, blood transfusions were a perilous endeavor, often akin to a coin toss between life and death. Physicians recognized the potential of transfusions to treat severe blood loss, yet the underlying reasons for their unpredictable success or catastrophic failure remained veiled in mystery. Some transfusions proved life-saving, while others triggered severe, often fatal, reactions characterized by fever, chills, jaundice and kidney failure. The prevailing ignorance surrounding blood compatibility transformed what promised to be a therapeutic miracle into a gamble with human lives. Landsteiner's seminal contribution stemmed from meticulous observation and a profound curiosity about the nature of blood. His experiments were straightforward in design, yet ingenious in execution. He collected blood samples from several individuals, separated the serum from the red blood cells, and then systematically mixed the serum of one person with the red blood cells of another. Through these simple mixing experiments, Landsteiner noticed a consistent pattern. The red blood cells from certain individuals would clump together or agglutinate when mixed with the serum of others. This agglutination phenomenon, previously dismissed as inconsequential, became the central focus of Landsteiner's investigation. His meticulous observations allowed him to classify human blood into three distinct groups, initially labeled A, E, and C. Group C was later renamed Group O. These groups were defined based on the observed agglutination reactions. Blood from individuals within the same group would not agglutinate when mixed, while mixing blood from different groups often resulted in clumping. This was the bedrock of Landsteiner's claim that human blood existed in distinct types, each characterized by unique surface properties. Landsteiner posited that the observed agglutination stemmed from the interaction between specific substances present on the surface of red blood cells, which he termed agglutinogens, and corresponding antibodies present in the serum, which he termed agglutinins. He theorized that individuals with type A blood possessed agglutinogens on their red blood cells and anti-B agglutinins in their serum. Conversely, individuals with type B blood had B agglutinogens on their red blood cells and anti-agglutinins in their serum. Those with type O blood possessed neither A nor B agglutinogens, but had both anti-A and anti-B agglutinins. The significance of Landsteiner's discovery lies in its explanation of transfusion reactions. When blood from incompatible groups was mixed, the agglutinins in the recipient's serum would react with the agglutinogens on the donor's red blood cells, triggering agglutination and a cascade of adverse physiological events. Understanding this mechanism provided a rational basis for avoiding incompatible transfusions and laid the foundation for safe blood transfusion practices. Landsteiner's work did not emerge in a vacuum. It was deeply rooted in the burgeoning field of immunology, which was rapidly advancing at the turn of the century. Scientists were beginning to unravel the complex interactions between antigens and antibodies, and the concept of specific immune responses was gaining traction. Paul Ehrlich's side chain theory, which proposed that cells possess specific receptors that bind to antigens, stimulating the production of antibodies, likely influenced Landsteiner's thinking. The side chain theory provided a conceptual framework for understanding how the body could distinguish between self and non-self and mount a targeted immune response. The immediate impact of Landsteiner's work, while significant, was tempered by the limited understanding of its full implications. While he had identified three distinct blood groups, it was Alfred von de Casello and Adriano Stelli who, in 1902, discovered a fourth blood group, AB. The discovery of the AB blood group completed the ABO blood group system and further refined the understanding of blood compatibility. Despite the initial limitations, Landsteiner's discovery furnished a rational framework for avoiding incompatible transfusions. This prevented many immediate fatalities and significantly improved the overall safety of blood transfusions. The enduring legacy of Landsteiner's 1901 paper extends far beyond transfusion medicine. His work laid the groundwork for the development of blood banking, a critical component of modern healthcare. It also spurred further research into blood group systems. This eventually led to the discovery of the Rh factor and other blood group antigens, each with its own clinical significance. ABO blood typing remains a cornerstone of modern medicine essential for safe transfusions. It is also utilized in forensic science for blood identification and paternity testing. Karl Landsteiner's 1901 paper continues to resonate showcasing the profound impact of careful observation and insightful experimentation. His work forever changed the course of medicine, saving countless lives and advancing our comprehension of human biology. In 1901, Karl Landsteiner published on agglutination phenomena of normal human blood. This groundbreaking work illuminated the immunological basis of blood groups. At its core, the paper detailed experiments demonstrating that blood serum from one individual could cause the red blood cells of another to clump together, a process known as agglutination. Through methodical observation of this phenomenon, Landsteiner discerned distinct patterns of agglutination, thereby defining the first three human blood groups A, B. Landsteiner's discovery hinged on the principle that red blood cells possess specific antigens, termed agglutinogens, on their surfaces. In the initial three groups, these were designated A and B. Individuals with type A blood possess the agglutinogen, those with type B possess the B agglutinogen, and those with type O possess neither. Crucially, Landsteiner observed that blood serum contains corresponding antibodies, or agglutinins. These were referred to as anti-A and anti-B. Type A individuals possess anti-B antibodies in their serum. Type B individuals possess anti-A antibodies. Type O individuals possess both anti-A and anti-B antibodies. The agglutination reaction occurs when agglutinins in the serum encounter corresponding agglutinogens on red blood cells. For instance, if type A blood is mixed with type B blood, the anti-antibodies in the type B serum will react with the agglutinogens on the type A red blood cells. This leads to clumping and potentially life-threatening complications if it occurs within the body during a blood transfusion. Landsteiner's work illuminated this fundamental immunological interaction, providing a framework for understanding blood group compatibility. The paper contains specific, tangible examples from the experiments conducted. Landsteiner described observing agglutination reactions when mixing serum from different individuals. He meticulously recorded the patterns of clumping, noting that certain serum samples caused agglutination in some blood samples but not others. These systematic observations allowed him to categorize blood into distinct groups based on their agglutination behavior. He also noted the absence of agglutination in specific combinations, indicating compatibility between certain blood types. These experimental results served as the empirical foundation for his conclusions. Following Landsteiner's initial discovery, Alfred von de Casello and Adriano Sterli identified the fourth blood group, AB, in 1902. Individuals with type AB blood possess both A and B agglutinogens but possess neither anti-A nor anti-B antibodies. The identification of the AB blood group completed the ABO blood group system. This established a comprehensive understanding of blood group compatibility. Transfusions could proceed safely, provided they adhered to the guidelines established by Landsteiner's research. Prior to Landsteiner's work, blood transfusions were often performed indiscriminately. They were dangerous procedures with unpredictable outcomes. Landsteiner's discovery provided a rational basis for ensuring transfusion compatibility by matching blood types. This simple yet profound understanding enabled the development of cross-matching procedures where donor and recipient blood samples are mixed to observe agglutination prior to transfusion. This prevented incompatible transfusions, a leading cause of morbidity and mortality. Landsteiner's 1901 paper sparked transformative advancements in immunology, genetics, and forensic science. His work laid the groundwork for the understanding of the molecular basis of blood groups. Genes encode enzymes that modify carbohydrate precursors on red blood cell surfaces, creating the A and B antigens. Individuals with type O blood possess a defective enzyme that fails to modify the precursor, resulting in the absence of A and B antigens. Landsteiner's discovery also paved the way for the identification of other blood group systems, such as the Rh factor, which is crucial in preventing hemolytic disease of the newborn. Subsequent scientists and researchers built upon Landsteiner's work, expanding our understanding of blood group systems and their clinical implications. His findings had a monumental impact on the fields of serology and immunology. It influenced organ transplantation, where matching blood types and other immunological factors is crucial for preventing rejection. The enduring impact of Landsteiner's 1901 paper endures through modern medicine. His observations and theories laid the foundation for safe blood transfusion practices. It contributed to our understanding of human biology, spanning immunology, genetics, and forensic science. The legacy of his work continues to save countless lives. It highlights the enduring relevance of his discovery in shaping modern medical practice.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.